imagine, if you will, that you're tasked with building this incredibly powerful, highly advanced AI agent. And, your mission is to automate a massive, complex chunk of your job.
Okay, sounds good so far.
Right. But the catch is, the only tools you actually have in your toolbox are like a roll of digital duct tape and a spool of twine.
Yeah, that sounds like a recipe for a very stressful workday, to say the least.
Oh, absolutely. And honestly, I think anyone who's spent a Tuesday afternoon trying to wrangle an autonomous coding agent knows that exact stress.
Oh, completely.
Because it's actually a pretty accurate description of how software developers are currently building Gen AI systems. They're essentially patching together these unbelievably sophisticated, totally unpredictable language models using standard programming languages. Languages that were fundamentally never designed to handle an intelligence that thinks or hallucinates or, makes its own decisions.
Right, which forces developers to rely on these incredibly fragile workarounds just to keep the AI from going totally off the rails.
Exactly. But what if we didn't have to do that? What if we could build an entirely new programming language from the ground up, designed specifically for AI agents?
Now that is the dream.
It is. And it's actually the premise of the source material we're pulling apart in our deep dive today. It's a really fascinating foundational paper titled Etas, an effect-typed language for agent systems.
Yeah, and to really understand the stakes of what the researchers behind Etas are proposing here, we really need to look at what a production-grade agent is required to do out in the wild.
Right.
Because a reliable AI agent, it needs to manage its own control flow. It needs memory, to remember what it did 5 minutes ago.
Which they often forget.
Exactly.
Yeah.
And it needs to reach out and access external tools like a web browser or a database. And crucially, it needs a way to actually recover when it inevitably makes a mistake.
Right. And the real problem right now is how we're currently giving them those abilities.
Yeah, we're basically using really messy framework conventions. Developers are taking standard languages, mostly Python or JavaScript, and using them to sort of glue these different components together.
Just taping it all up.
Right. They're not using semantic language rules that a compiler, the engine that turns human-readable code into actual machine instructions, can actually understand.
So the mission for our deep dive today is to explore this radical shift that the Etas paper presents. We're going to look at what happens when you just stop trying to hack AI into existing languages and instead give these agents a native home.
I love that phrasing, a native home.
Yeah. But to really grasp the mechanics of Etas, I think we need to spend a little time looking at the trap we're currently stuck in.
Yeah, the paper actually calls it the framework trap, which is a really great way to think about it.
Okay, tell me about the trap.
So if you want to build an AI agent today, you probably reach for a framework like LangGraph or AutoGen or LangChain. And these tools are incredibly popular and for good reason, right? They make it relatively easy to get started.
Sure, they lower the barrier to entry.
Exactly. But underneath the hood, they're just running ordinary host language code. They take things like prompt templates, tool registries, logging mechanisms, and they just wrap them in standard Python or JavaScript objects.
So, meaning the AI agent isn't actually a fundamental part of the programming language?
No, not at all.
It's kind of just a Python callback function wearing a fake mustache, like pretending to be an agent?
That is exactly what it is, and that illusion leads to a massive structural problem.
How so?
Well, in a standard framework, questions that really should be answered mathematically by the programming language itself are instead answered by operational logs or naming conventions that a human developer just has to manually enforce.
Okay, let's ground this in a real scenario for the listener. So if I'm a developer and I'm trying to build a classic, like, draft, approve, publish workflow,
Okay, yeah.
where, say, the AI drafts a report, a human manager approves it, and then the system emails it out to the whole company. How does the framework trap actually bite me there?
Okay, so if you build that workflow in a framework like LangGraph, you construct what the framework calls a state graph. The code you write shows the state schema and the order of the nodes. You're literally just drawing a path from the draft node to the publish node.
Which, that seems totally logical to me. I can look at the code and see the exact path the AI is supposed to take, right?
Right. It looks logical to you, the human who's reading the code, but the compiler has absolutely no idea what is actually happening inside those nodes.
Oh, I see.
Yeah, the framework's graph, it exposes the order the callbacks are supposed to fire in, but it does not expose the fact that the publish node actually requires permission to use the company email server. or that a human approval is mandatory before that email function is even triggered.
Wow.
Yeah. All of that critical high-stakes logic is just hidden away inside a generic Python function.
So building an agent in Python today is kind of like installing a jet engine on a bicycle.
Oh, that's a great analogy.
Like, the bicycle frame has absolutely no structural awareness of what kind of thrust is about to hit it. You're just strapping it down and, like, praying the bolts hold when the AI hits the gas.
And honestly, you're usually finding out the bolts didn't hold when the bicycle is already airborne.
Exactly.
But Etas, on the other hand, is like actually building a fighter jet from scratch. The frame is structurally aware of the engine because it was explicitly designed around it.
Right, and the Etas paper talks a lot about making agents what they call first-class semantic constructs,
Yes,
which we should probably break down what that actually means, because that sounds like some heavy computer science jargon.
it does. But essentially, a first-class citizen in a programming language is an entity that the language natively understands and can manipulate without special workarounds.
Okay, so like a number.
Yeah, exactly. In Python, an integer is a first-class citizen. The language just inherently knows what a number is, how to add it, how to store it. So in Etas, things like agents, model callable tools, prompt values, typed memory, human approvals, they're all granted that same native status.
Okay, so going back to that draft approve publish workflow, if I write that in Etas, I'm not hiding the email action inside some generic function.
Right.
The model inference, the email authority, the approval policy, those are actual source-level facts.
Exactly. The compiler can look at the raw Etas code and say, okay, I see that this flow requires the company email action, and I see mathematically that it is governed by a publish policy.
That makes so much sense.
Yeah, and because Etas sees the agent's structure natively, the compiler can strictly enforce what the agent is actually allowed to do, rather than a developer just having to guess based on operational logs after the code has already run and, potentially failed.
Okay, I definitely see the appeal of having the compiler act as this strict manager, but here's where I get hung up, honestly.
I'd lay it on me.
If Etas treats these actions, like sending an email or writing a file to a server, as native parts of the language, how does it physically track and control what the AI model might actually try to do? Because we all know these large language models have a total mind of their own. They hallucinate entirely new tool commands, like all the time.
Yeah, they really do.
Yeah.
And you are hitting on the main vulnerability there, which brings us to really the core technical innovation of the paper, this strict separation of effects and traces.
Okay, I'm going to need a deep dive into how those two things are different.
All right, so in the architecture of Etas, an escaping effect is the actual tangible external authority needed to do something out in the real world.
Like actually sending the email.
Yes, actually sending an email over the network, or physically writing a file to the hard drive, or charging a credit card. That's the effect. A requested action trace, on the other hand, is this unerasable audit record of what the program asked to do, regardless of whether the action was actually permitted to happen.
Okay, wait, I have to push back here for a second.
Go for it.
Isn't a requested action trace just like a fancy academic phrase for a log file?
Not quite, no.
Because I feel like I could write a killer Python logging script that records every single thing my agent asks to do. So why do I need a whole new programming language just to keep a record?
It's a fair question, but the difference is that standard Python logs are written after the fact. A log file is something you read during a post-mortem to figure out why your AI just, emailed your entire customer base an internal strategy document.
Fair point, yeah. That's usually when I check the logs.
Exactly. And if the program crashes halfway through, or if a developer accidentally deletes the log command, the record is just completely gone. But in Etas, the compiler demands that the trace exists as a fundamental condition of the code compiling at all.
Oh, wow. So it's an intrinsic property of the code itself, not just an afterthought.
Exactly. Let's look at the paper's specific example of a dry run email handler. So say you're building a test suite for your agent. Obviously, you don't want to actually spam real people during testing.
No, definitely not.
So you set up a mock handler. It intercepts the agent's request to send an email. No real email is sent to the outside world.
Right, that's pretty standard testing procedure. The mock intercepts it, the test passes, the system moves on.
Right. And in a traditional framework, because the email was mocked, the caller's obligation is basically handled. The external effect never happened, so the system essentially forgets the attempt was ever made.
Sure.
But in Etas, a handler cannot grant authority. It can only interpret requests. So even though the physical email wasn't sent, the fact that the agent attempted to send an email remains permanently burned into the requested action trace.
Oh, I see. So a mock handler can't erase the fact that the agent attempted the action in the first place. The compiler still sees the mathematical fingerprint of the request.
Yes. The trace serves as mathematical proof that the program asked for email authority. And that is critical for security audits, for enforcing overarching policies, and just for safely replaying the agent's actions later. Yeah, the request remains fully visible to the system's policy engine, even when the real-world effect is completely hidden.
Okay, so Etas is tracking every single request natively in this unerasable trace. But how does it actually enforce the rules? Like, how does it look at that trace and physically stop the agent from doing something malicious?
Okay, this is where we get into the heavy lifting of what they call compile time specs and residual checks. Etas uses specifications as strict compile time constraints.
Let's break down the syntax of one of those specs, because I know the paper uses a very specific format.
Right, so take the approval policy we discussed earlier. In Etas, you write a trace spec that looks like this: approval.request and then 2 arrows pointing to the right, followed by company email.send work account.
I see. So those 2 little arrows pointing to the right, that signifies that the approval request literally has to occur chronologically before the email sent.
Exactly. It is a non-negotiable temporal obligation. And the compiler translates those arrows and commands into what the paper calls trace spec algebra monitors.
Trace spec algebra. Okay, we're throwing a lot of syllables around today.
We really are.
What does that actually look like in practice? Like, how does it work?
Think of a trace spec algebra monitor like a digital subway map for the AI. The compiler maps out every possible sequence of stops the AI train can make based on the code you wrote.
Okay, I like this analogy.
Yeah, it calculates all the branches and intersections mathematically. So if the compiler sees that there is a possible route where the AI train can go directly from the draft station to the send email station without physically passing through the get human approval station, it flags it as an illegal route.
And because this is a compiled language, it doesn't just send, like, a Slack warning to a dashboard. It stops the train before it even leaves the station.
Exactly.
The code literally will not compile.
Right. The static analysis physically sees the untethered logic and just refuses to build the executable program. It says, I cannot prove statically that an approval will always happen first, therefore this program is completely unsafe to run.
But hold on a second.
Yeah.
How can the compiler know everything in advance? What if the safety of an action depends on something that only happens while the program is actually running?
Oh, right.
Like, what if the human approval has a time limit?
Yep.
Right? And it expired 5 minutes ago. The compiler can't predict time passing before the code is even executed.
No, it can't. And that is exactly where residual checks come in. You're totally right. The compiler isn't psychic. If it cannot guarantee safety statically because it depends on dynamic runtime data like an expiration timer or maybe an AI choosing a totally random file path dynamically, it doesn't just crash.
Right, that would be terrible.
And it certainly doesn't just blindly trust the agent and allow the action either. Instead, the compiler emits a residual check. It takes that unproven obligation and makes it an explicit mandatory hurdle at runtime.
So a residual check is basically like a bouncer at a nightclub.
Oh, I like that.
Right, so the compiler maps out the clubs, but it puts a bouncer at the VI key door. Even if the AI manages to navigate the club and tries to sneak past, the bouncer demands to see ID, which is the real-time dynamic data, before letting the action through.
Yes.
And if the AI doesn't have the current unexpired approval, the bouncer just tosses it out.
That analogy perfectly captures the mechanism. The compiler sets up these bouncers everywhere there is dynamic uncertainty. And what's really crucial about this architecture is that it entirely prevents hidden authority.
What do you mean by that?
Every action an agent can take must be explicitly declared in its escaping row, which is basically the agent's official VIP guest list of allowed actions. It's strictly deny by default.
So, if the language model hallucinates and suddenly outputs a command to execute, say, a shell script, and shell.exec isn't on that declared guest list,
it hits a solid brick wall, the request is denied by the runtime environment, a severe error is raised, and the attempt is permanently logged in the trace.
Wow.
The agent physically lacks the vocabulary within the language to force the command through.
So the bicycle finally has a frame built specifically to handle the jet engine.
It really does.
That's amazing. We've spent a lot of time looking under the hood at the theory here, but let's put this all together for the listener. If you're listening to this and you're trying to build an automated workflow tomorrow, What does this actually change for you?
Good question.
Because the paper outlines 4 specific case studies that address massive headaches developers face today. Let's kind of weave those together. Say I'm deploying an agent tomorrow to write our company's internal newsletter.
Okay, so the first hurdle you're going to face is what the paper calls context engineering. And this is essentially how you manage the flow of information you feed into the AI's prompt.
Because if my AI is like sorting through our company's entire Google Drive to find news, one hallucination means that AI might accidentally grab a highly confidential document, let's say a document titled Q3 Layoff Strategy.
Yikes.
Right, and paste the entire contents into the newsletter prompt.
Yeah, and in Python, you have to write all these convoluted validation scripts to try and catch that before it happens. But in Etas, memory regions are typed and effectful. So you explicitly grant the agent read access to the project memory.news region, but you actively deny access to project memory secrets.
Meaning, Etas fundamentally blinds the AI to that confidential document at the language level.
Exactly.
The AI literally lacks the semantic pathway to even perceive the secrets folder. So the compiler prevents secret leakage into a prompt before the code even runs.
That handles the context perfectly, but once your AI has the right data, how do you make sure it behaves?
Right.
That brings us to harness engineering. This is about defining the runtime substrate around the model, the exact tools it is allowed to use.
Right, because I definitely don't want my newsletter AI deciding it needs to delete server logs to make room on the hard drive.
Exactly. In a traditional framework, you might pass a list of tool functions to an agent and just kind of hope it sticks to the list. In Etas, you explicitly define the tool surface at the source level. You write syntax that explicitly denies dangerous actions, like -shell.exec, while allowing safe ones, like plus newsletter.draft. It's a highly specific permissions manifest built right into the core syntax.
Okay, so it can't read our secrets, and it can't run shell scripts. But what if the AI just gets stuck? Because anyone who has built an autonomous agent knows they love to get trapped in infinite loops.
Ooh, they love a good infinite loop.
It hits a broken link while researching the newsletter, and it just keeps trying to fetch it over and over and over.
Yeah, this is loop engineering, and it is a massive financial risk. I mean, developers frequently wake up to $5,000 bills from API providers because their agent spent the entire night trapped in a repair loop trying to fix a single typo.
Painful.
Very. But Etas addresses this by allowing developers to set up bounded repair loops with explicit temporal rules and interpreter-enforced budgets.
Wait, I can tell the language itself to cut the AI off.
You can. You can write a trace spec that caps the loop at exactly 6 attempts and say a maximum spend of 60,000 tokens. Once it hits that limit, the language runtime physically halts the execution.
That is huge.
Right. It isn't an external script tracking your API usage. The interpreter itself acts as the accountant and enforces the contract.
Wow.
Furthermore, in coding scenarios, you can mandate that a CI.run, basically a test DAC and a human review.request, must occur before the AI is even allowed to execute a repo.merge into your protected main codebase.
So the agent physically cannot merge broken code without testing and review, no matter what its internal logic decides.
Never.
Okay, that covers the safety, the context, the harnessing. But there is a fourth aspect here that really changes the game, and that's optimization. Is Etas not just making agents safer, but actually making them significantly cheaper and faster to run?
It does, and the mechanics of how it achieves that speed are honestly fascinating. Because Etas treats all these constraints and tools as first-class citizens, the compiler has a holistic mathematical view of the entire workflow. So imagine your newsletter agent is doing research, and the compiler sees that its tool surface is strictly narrowed down to just one action, archive.search.
So the compiler knows this agent is only allowed to search the archive. It can't, like, browse the open web.
Exactly. And because the compiler forces developers to explicitly declare data dependencies using its type system, the compiler can look at the code and recognize if a search query is loop invariant.
Meaning the agent is asking the exact same question in multiple iterations of a loop. Like, what were the sales numbers for Q1? What were the sales numbers for Q1?
Yes. So instead of letting the agent ping the API 10 separate times for the exact same search, which is just wasting money and time, the compiler automatically hoists that search out of the loop.
Oh, that's smart.
It runs the search once, caches the result, and just feeds it to the agent whenever it asks. Furthermore, if the compiler's static analysis physically sees that the agent is running 2 independent research iterations that are completely untethered.
Meaning task A doesn't require the output of task B to function.
Exactly. It can automatically spin them up to run concurrently in parallel.
That is wild. It deduplicates repetitive tasks and parallelizes the workflow automatically without me having to write any complex asynchronous code.
And it does all of this without weakening any of the safety guarantees we just discussed. The trace specs and residual checks still apply perfectly, but the execution becomes vastly more efficient.
Incredible.
This kind of deep optimization is incredibly difficult to pull off safely in a traditional Python framework because the framework has to constantly guess what the agent might do next. Etas doesn't have to guess. Etas just knows.
It really is the difference between trying to direct city traffic while blindfolded versus having a bird's eye view of the entire grid.
Yeah, that's a perfect way to put it.
Let's pull all of these threads together. What we're seeing here with Etas is a fundamental paradigm shift in how we approach artificial intelligence. For the past couple of years, we've been desperately trying to force AI to play by the rules of legacy programming. We've been wrapping it in layers of Python and JavaScript, just hoping the digital duct tape holds when the system goes live.
Yeah, and the paper makes a really compelling argument that agent system safety, auditability, and efficiency shouldn't be things we try to scrape together from messy log files after a disaster already happens.
Right.
They must be woven into the language interface itself. They need to be checked mathematically by compilers and enforced ruthlessly by runtimes.
And for you listening, whether you're prepping for a high-stakes meeting on how your enterprise is going to integrate AI workflows, or you're a developer dealing with the daily headaches of current frameworks, understanding this shift matters.
Absolutely.
Knowing the difference between a framework and an agent-native language gives you a massive advantage. It is a clear window into how the next generation of truly reliable enterprise-grade AI is actually going to be built. We're finally moving away from the era of hacking things together and entering the era of purpose-built semantic engineering.
It is a totally necessary evolution as we give autonomous agents more authority over critical systems, from managing finances to writing production code. The language they run on must be fundamentally capable of governing them natively.
Which leaves me with a final, slightly mind-bending thought to mull over.
Okay, I'm ready.
If programming languages are now being built from the ground up to natively handle the pure, chaotic non-determinism of AI models,
Yeah.
if a language can perfectly track, govern, and constrain an AI's every single action using trace-speak algebra and bouncers at the door, what happens to the concept of a bug?
Oh, man, that is a fascinating philosophical question.
Right. If the Etas compiler ensures mathematically that the agent absolutely cannot send the email without the approval and cannot access the secrets folder, does it even matter if the AI's internal logic is a complete black box?
That's the million-dollar question.
If the digital duct tape is replaced by a perfectly engineered titanium cage, maybe we don't need to perfectly understand the ghost in the machine anymore. We just need to design the perfect cage.
That's wild to think about.
Something to think about on your commute. Thanks for joining us for this deep dive. We'll catch you on the next one.